So in this video, we're finally going to talk about tasks and await and async. They're kind of the key thing in C# for doing any task work, which basically means when you see, say, a public function that returns a task, and you do work, and then typically a task would have an async, and inside it would await something. And you'd have something similar to this. So this setup, this task setup. So that's what we're going to talk about in this video. I'm going to try and keep it sectioned and organized, and most of it will be explanations more so than code. We'll obviously do code examples, but there's also going to be a lot of conversation going on about what what things are, and so you can fully understand tasks. So I've done the previous 2 videos on threads, so hopefully you understand multi-threading now, which is very important for tasks and how tasks work, because ultimately they make heavy use of threads. So hopefully you're gonna understand that concept. So the first thing we want to talk about is, firstly, what is asynchronous? What does the word actually mean? So the word asynchronous basically means if you start something and you don't wait while it's happening, you don't wait for it to finish. And it literally means to not occur at the same time. So that's what asynchronous actually means, as opposed to synchronous, which means everything happens and waits for the previous action to complete before it moves on. So asynchronous basically means that it doesn't mean that our code returns early, but rather it simply doesn't sit there blocking the code while it waits. So it doesn't block a thread, talking from a code standpoint. So I'll dump that kind of description in here as we go, and I'll share this project as part of this video, because there's going to be a lot of description, so at least you can kind of read through a project as you go. So that's issue 1, if you will, or rather topic 1, which is what is asynchronous. The next topic is going to be the issue with using threads, because we know threads are asynchronous. So we're describing what asynchronous is, but we're talking about tasks. So now it's a case of, well, we can do asynchronous work with threads. So why don't we? What's the issue with threads? So firstly, why are threads asynchronous? We've described asynchronous, and I'm saying they are, so let's break it down and describe why. So threads are asynchronous as they naturally do something while the calling thread that made them doesn't wait for it. So we can show that with a code example. So if we first dump my little statement there, and now we'll do a code example. So if we do console.writeLine before first thread, and we do another one that says after first thread, we get rid of this return here. And then in here we do new thread, and inside the thread we then start, and we simply say inside first thread. And let's do, in order to separate this up, to show this, we want to show that this doesn't wait for this, so we'll put a simple thread sleep here of, say, 500 milliseconds. And then in order to clear off for the next example, after this fact, we'll do a thread sleep of like a second, just to make sure that anything that we do after this point, this doesn't come in afterwards. So if we were to run that example, and hopefully this is going to open up on the right screen, because it never seems to open up on the right screen. And of course it doesn't. Let me just put a console.readline so it doesn't close. Put a breakpoint. I'll have to keep doing the same thing I did in the last video until I fix this issue. So the window keeps opening on me second screen. So here's the window, and this is going to be really annoying actually. Let me see if I can fix this again. Okay, so if we run this example, you can see we get hello world before first line, after first line, and then inside thread, which means that the order has gone here to here, and this is ran independently, which we discussed in the thread video. So that is why threads are asynchronous, because they run, the caller doesn't wait for the action itself to run, which is what we've described above. So that describes why threads are asynchronous. So now it's, what's the issue with them? So the first issue is doing a new thread is an expensive operation. Creating a thread consumes memory on the heap. It consumes RAM. It consumes process. It takes maybe almost a megabyte of RAM to keep a thread in memory and to keep the whole state. And it also bogs down the system that has to switch between threads. The more threads there are, even if they're not being used, it has to evaluate every thread to find out which one's available. So threads are an expensive operation. You don't typically want to make a new thread for every little operation. That's issue one. Issue two is it's not natural to be able to resume after this thread is finished back here, if you will, without blocking this thread. So it's not a natural way and an easy way that we want a single nice clean one-liner to say, do this work here on a separate thread, but then carry on here, because that's how we look at code. We want to see it line by line and understand it line by line. So threads are not a natural, they're not very natural at being able to be useful in an asynchronous world where you want to await them. You want to wait for something to happen. So let me just chuck those two issues into the description, so we can, like I say, keep an eye on going forward with this. So let me just chuck this description here, and now we'll work on issue one is expensive to make. So the way this was solved is that they created something called a thread pool, and a thread pool simply is used to queue worker items. So if we do thread pool, you got queue new worker item. So this is then you can spin up an object to do some work, and all that does is it goes in, and if there's no threads that have ever been used, it does a new thread because we need a thread. But then once this work's finished, the thread pool keeps hold of that thread for a little while, or until it determines it's using too much memory and it cleans it up. But what the thread pool then ultimately does is keeps a living pool, a living collection of threads that can be consumed by anyone wanting to do work. So it's like you run 3 operations, and the second operation starts a second after. So this thread has since finished, and instead of it being disposed and then creating a brand new thread, it gets recycled and reused because it's since become idle. So the thread pool solves issue one. However, issue two is still an issue for threads, and there's no real clean and easy way to do this, and that's why tasks were made. So in order to resume work after some asynchronous operation has occurred in a thread, then there's a few options that people have done for years, obviously until tasks were about. And one would be to simply block the calling code. So, block this with something similar to this. So in fact, let me do an example in code. So let me just first, again, take what we've described and dump it in. And we will do some code example. So if I just paste this in here, and we want to talk about specifically what had happened here. So if we were to block the thread, we would have to do a new thread, and we would do var blocking thread as a new thread inside blocking thread. And we don't start it straight away because we want the thread. Then you can do blocking thread.start, and the way that we block your code to wait, we do basically a blocking thread.join. And this is one way of doing the solution, if you will. So this would now be after blocking thread, and we do before blocking thread. And hopefully these kind of examples are going to be useful, because then you can simply run them all and you've got a single code file to kind of see what's going on. So we'll have the first inside and before, and then here now you've got before the blocking thread, and you can see inside blocking thread and after blocking thread. So it's literally blocked our thread in an inefficient way. So this thread that we're on is no longer of any use, because while it's waiting for this thread, it's effectively fully blocked. So this is almost a completely pointless piece of code, because all you've done now is created a second thread, but consumed 2 full threads to do one piece of work that could have been done on 1 thread in the first place. So this is effectively not really a solution in any sense. It's completely useless. So that's obviously not a solution. The second way of doing it is to constantly poll for completion while waiting for, say a flag to be set in a loop. And this has the same kind of issues because there's so many ways of doing it, and there's not necessarily the way you would do it as the way I'll show you, but to get the point across, it's exactly the same. And let me, in fact, wrap the code samples up so the comments are clean. So there's issues, or rather, threads are asynchronous. There we go. And we'll just wrap this bit in. And then we've got code samples then kind of embedded in the comments, so it's nice and clean. So blocking thread, or blocking wait, let's call it. And that will go to here. And then in order to do the callback style, like constantly polling, so we'll say before polling thread. And like I say, there's many ways of doing this. This is not necessarily how it was done, but it simply proves the exact same point of the fact that it's inefficient anyway. No matter what you did, you're still effectively locked for the most part into the thread. So this would say poll inside polling thread, and then we would start, and this time we don't join. So now instead, poll for completion. So you'd basically do while, well, one way we could do it is we'd have var poll complete equals false, and then once we're done, say polling thread complete. Or rather, we don't need to say it there, we can just do it. Poll complete equals true. Set complete. And again, there's many ways of doing this. You might want to use a task, well, not necessarily a task completion source, but reset events or timers or anything. But again, that's not important in this sort of description. It's simply showing the point of one way it might happen. So you could say while not poll complete, so while it's still running, you can do, say, thread.sleep. You can do anything. You don't necessarily have to do thread.sleep. And you'd sit and you'd kind of poll for, this permanent loop. And you could do work in here, some work, but in essence, you're waiting a set amount of time. And if that time was, say, a second at a time, then this could have been finished for half a second before you even do things. So there's many issues with doing this way. So this is after polling thread. And you could even put, if you really wanted to be, kind of see what's going on, then you'd remove this. I'll comment this bit out. But you could say, to see it physically happening, you could put that there, say, let's just change this to, say, 50 so it doesn't happen that many times. And then if we run this example, you'll see inside first thread, and then you've got polling, inside polling thread, does a bunch of polls, and then it's after. So it's the same kind of issue. Your thread's ultimately stuck whatever you do. You're simply polling for completion. You could do a... well, the next thing we'll do is an event-based callback, but this is the way you'd poll. You'd literally sit and wait for it. So change that to just 100 so we can leave it in the example, actually. So it keeps it clean. So that's a second way of trying to, solve this issue of waiting for it to complete and then resuming on the thread that we want to do work on. And as I mentioned, there's the issues with that. So the third step is, or the third way of trying to solve this is event-based callbacks. So this is very similar to polling in one sense, but this is going to introduce something else into the mix, which we'll see in a minute. So we have event-based waiting. So this before event thread, we don't need that. This would be event thread. Inside event thread, doing something, and then fire completed event. Now this would obviously be done slightly different, but again, for the point of example, it doesn't really matter. This would be after event thread. And now here we need to make an event to fire. So by default, we'd have typically, you'd have an object or a class or something that you'd register to. You wouldn't necessarily start a thread. This would be a class that maybe contains a run action that does a thread, or, again, the only point that matters is the way in which we do, the point of event-based callback, what happens in the callback when something's run. So the simplest way I can show that is to make an event directly. So let's just go up to the top here and just do private static event that just does nothing, just an action. You can just do event finished and create a blank event so we don't have to new it up. And then all we can do in here, and again, like I said, this is not how it would be done necessarily, but it proves the point. We would, before the event starts, you typically create the thread that usually hold the event, or create the class that holds the event, and then we'd hook into event. So you'd say, and again, like I said, this is not how it would be done, but it kind of shows what would happen. It's the exact same principle. You're listening on an event. So we'd have event finished plus equals, and then this is our now callback, if you will. So callback from thread. And then in here, we'll just chuck in, that is rather after event thread. This is event thread called callback on complete, say, to show that this is what happens once it's done. So then here, fire completed event would be literally to say the event's finished. You inform any listeners of the event. So what's happening here is we create a new thread. We hook into an event that's right now not necessarily linked to this. It doesn't really matter. We create a thread, hook into an event. We start the thread, and then we state that we're now here. So our code will run there to there, hook into here, run those two lines, and end up here. Once it hits here, so we'll step through to show you that, then that's this thread done and waiting, if you will. It's now this thread's idle waiting here. At that point, then this thread runs in parallel and starts doing this work. So we'll go inside the thread, it'll wait, and then it'll finally go fire off an event. And then because we're listening here, this event will cause us to hook into here and end up firing this call here. So what you should see is before event, after event, and then you'll go inside event and then the callback. And I'll show you the kind of stepping through in code just to let you see that. So we go before event, the thread's ready, we hooked in, we start the thread, and it's after. And now we're at the read line. And then you can see if we rerun that now without breakpoints, just so you can see it happening directly. So you have the before event thread, after event thread, which you mentioned. So now that thread's fully done. Then you're inside the event thread, and the event thread callback on complete. So you can kind of see that happening. So that's one way of doing it. And you can then encapsulate this into sort of a function. So if we were to do, say, a private static void event thread callback method, and you could just have event, or you could even have an action completed and do a callback in this fashion, then this would do the same work as this thread. So we do nothing different in essence here. We just simply do a inside event thread method, and we wait, and then we fire the completed event, then we say completed. So this is another way of doing the exact same thing. So event-based wait, and copy and paste event-based wait method. And then this way, before event method thread, and then you wouldn't have any of this because it's now a method that contains all the work. So you'd simply say event thread method callback, and your callback is now directly in here like this. So that's the hook, if you will, is by passing in a lambda action to call back. So it's doing nothing different. We've simply moved the logic into a method, and this is what it would then look like. So if we ran that code, you'll see exactly the same action happening, no different. Apart from we tried to start a thread that we didn't create. Left that line of code in there. So you can see then you've got the before event thread, after, and then you can see also before event method and inside event thread. I don't know what we haven't done. We should also wait, as I mentioned. Once we're doing anything that kind of holds and waits, let's chuck a second delay to let that clear off, so we don't get this kind of cross-contamination of things happening. And also, I should probably chuck in like a nice long thing on the befores and afters, or rather just on the afters, so that we have a nice separation to visually see the difference in all these examples. So let me just chuck this line of code every time we do an after. And this one will also want the oh, that's not right. Good job I noticed that. Sleep after the fact again to get past that. So now, if we run, we should have slightly clearer output. So there's the blocking example, there's the polling example, there's before and after the event thread, and in fact, we should move that sleep inside so that the layout stays correct. That one we also haven't waited for some reason. Oh, because we're polling, we don't need to wait for that one. The blocking we don't need to wait for, so it was just that one mainly, and this one. And then we should have a nice clean separation of what's happening where. There we go, so you can now see the order nice and easy. So before event thread, after event thread, inside, and then callback, and then before. And in this case, we've got inside, event thread, and after. So we've actually got something different going on here, which is obviously because I've done this wrong. It's not what we'd do. This would typically be a task, or rather a thread. So as we mentioned, it's kind of showing the same example here of what I was doing, and that is just to, start a new thread up. I was moving the logic inside a function, so it was meant to be that, which now should give us the same result. So you see before, after, inside, callback, before, after, inside, callback. So these two are the same, just one's done in a method and the other one's done directly in line to show you the point. So in order to see, though, the issue with what's going on here, we have a slide to show here where we change threads, which is important when you're in like UI applications. So there's a significant change here in what's happened with the action that's running, because in the polling and the blocking, you're physically on the same thread, and when you're finished, you resume on the same thread because you've never gone off it. With the event-based callbacks, the callback is happening here on a different thread. So it's not really obvious until we start logging some output with showing threads. So let me just chuck in a helper. So private static void log, and then we'll have the message, and then we're going to have the console.writeLine message, but we also want to output the current thread run so we can see. So the current thread will simply put in little square brackets, and we'll do thread.currentThread.manageThreadID, and this will output a message with the current thread ID appended. And I should also comment these codes. I know it's an example, but this is a useful example, so we want to comment everything. Shows an event-based thread callback via a method. Callback to call once the method is complete, or once the work is complete more specifically. Start a new thread, log it. So now all these will change to log, instead of this, so we get the output inside, sleep, and then fire event completed. So that's that. I'm happy with now. We've got comments. Everywhere in here we want to change to log, so we'll even change the hello world to log to get the output. I'll say log it, threads and asynchronous, log, or wait for work to finish. That one is really. So that will log, this will log, this will. Start new thread, sleep a little, log it, log after, wait. So that's just showing threads asynchronous. The blocking call, log, create new thread this time, sleep a little, start thread, block and wait, log. And the only difference here is we don't need to log the ... We're not, we don't really care where that this happens. This is purely for splitting up the areas cleanly. So this one's log again, create poll flag, create thread, sleep a little, and then set flag complete. Start thread, poll for completion, log while we're waiting, sleep a little. Nearly done now. 2 more left, and then this will show you the output now, which will start introducing the, what thread we're on, and we can start thinking about things as in a true multi-threaded application and really getting our heads around what's happening and the difference. Event took turn, callback. And then what did we write for the last one that kind of waited? I think it was a polling one, event-based one. Oh, this is the first time. I thought we'd done a wait for work to be completed. Oh, that was up here. Wait for work to finish, we said. So that'll be there. Wait for work to finish. And event-based, last one. Should have just commented at the start instead of having to go back, but I was trying to talk through examples to get us going. So, call method. And then the callback is here, which we also log. And then we said, what was it? Wait for work to finish. That was it. Right, and so now the only difference here is we should see the current thread where everything's running on, which is now useful for us explaining things. So let's go back and just explain a few things. We've done this in the last video explaining threads, so it should be obvious. So your main thread when you start your console is thread ID 1. And then you can see everywhere where it's running on thread 1 then, and you can get a view for that. So in terms of the code, we don't need to step through all of this. We've done it. We're before and after the first thread, and then we know this other thread runs on its own thread ID. It's a new thread. And that's what it is. We know that. And then we get to the blocking thread, which is, in fact, the first thread needs a separation. first thread and blocking thread are two separate things. So that needs a separation there. So the first example simply shows that I've done it again. Put that before the sleep, not after. Right, so the first one is showing simple asynchronicity, which is before and after the thread is thread 1. Thread 1 then carries on here ultimately, but on a separate thread, this gets run. Then the blocking shows that this gets called, then we wait for thread 4 to complete, then we carry on. The polling shows a similar thing. We start on thread 1, we poll on thread 1, while thread 5 starts running the work, and we sit there polling, and then when we're finished, we're on thread 1. So ultimately what we're noticing here is after the work's done, or rather when the work's complete, the thing we want to run after work's complete. So far as thread 1, we simply didn't wait there, thread 1. And then we move now onto the event-based, and you'll see the difference. So now in the event-based, before and after the thread are on thread 1, then the thread starts running, but now the callback, when the work's complete, importantly, is actually run on the same thread as the action, the method that was being run asynchronously. So once we've finished working on this thread, in an event-based callback, it means that our callback thread that we might expect to be on the same thread, for example in UI, if you want to wait for an action to complete and then set some text in a text box, you're going to be coming back on the wrong thread. You're not resuming back on thread 1. So this is the key important difference with event-based callback, and you needed to understand, you need to, one, see that happening, and two, understand, if you watch the last videos about threads and the UI thread and why you have to be on the UI thread to change UI elements. So this is an important issue, if you will, or at least an important style or thing that happens with event-based callbacks. We now lose the calling thread. So that's kind of the issue there, if you will. So we've got issue with this, issue with this, issue with this. And what we're trying to show here is why tasks were created. So I know we're still on threads at the minute, and I'm sure you're eager to get to tasks, but it's also important to understand why tasks were made and why threads aren't suited for it, what issues you get with using threads as opposed to tasks. So the last one, to be honest, the last issue I had was function callbacks, which really is what this is. So really there's only 3 ways of doing it, or the most common ones are 3 ways of doing it, because this is the same thing. I've just styled it slightly different. So obviously what this also means is that every time you want to do, and another issue rather with, let's say, this event-based style callback, where, let's take the method one, it's a bit cleaner. Say now, once we've called back and then here we want to do something else, what are the thing we want to do as a callback? What you then end up with is, oh, the thing I wanted to do as a callback, and I'll do something in here. And then the thing I want to do with that as a callback. And what you start getting is these nested callbacks, when your code ends up getting deeper and deeper and deeper into a nest, which is not what you want. You want to try and avoid the nesting situation. So loses context, calling thread on callback, and causes nesting. So that's what we'll comment there. So this as a whole is issues with threads. Let's also make this a little bit clearer with titles. And I want this to be as much a document as it is a piece of code. So like I say, you can pick this up, read through, and understand the principles. So basically the other issue, or rather the issue overall with these threads, as you can see, is basically however you make the way of getting a callback to do something after something's awaited, there's a lot of code, or there's a lot of like workarounds or non-clean code. And that's ultimately the issue. So if I just dump that little statement in as a finishing statement of kind of, where the issue is with threads. And that's really the main issue with threads. So this next really brings us on to what is a task, I guess. So if we just copy the title, paste it in here, change this to what is a task. Also notice that needs an extra bit there. There we go. So what is a task? So basically a task is, in its simplest one line, when I only want to describe it in one line, I don't want to make it confusing because it isn't. A task encapsulates the promise that an operation will complete in the future, which is ultimately what all this is about. So a task is defining that because a task is an object that we return. So it's a physical object we can make use of. The object itself is the promise of work to be completed in the future. So we're returning not necessarily a thread, we're returning an object that's representing that a piece of work will be complete in the future, and we can subscribe to await for that to complete and resume. So that's ultimately what a task object is, and it is a true object and it does get returned. So task encapsulates the promise. I'm actually slower at typing when I'm talking. Promise of an operation completing in the future. And that's all there is to it. That's all we're going to say about a task. That's what a task is. So that will bring us on to the tasks, async, and await keywords, which I think will be not necessarily, well, yeah, it's its own header, I guess. So this would be tasks, async, and await. And in here, then, we can start our work on async. So async in C# is mainly two words. So those words are async and await. And the point is to allow easy and clean asynchronous code to be written without complex and messy code. So basically, it's to do what we've done here, and in all these examples, in a more efficient and code clean way. So you don't have to write all this boilerplate code. So that's the point of, this, if you will. So let's see this in action. We want to see basically what synchronous code looks like compared to asynchronous. So it's time to actually see the word async and await in action. So the simplest example I can find, or rather I can think of, if we make these helper methods, can't type very well today. This is thread helpers. Well, it's not really helpers, it's thread methods, so we're just simply using it in the thread section. And now we'll have task example methods. So the simplest thing I can think of to show an example is, let's say, what should we call it? Web download string. And we'll pass in an URL. Downloads a string from a website URL. Synchronously. There we go. URL to download. So that's just a normal function that you've seen before, and this is a sync pattern. A synchronous pattern. And for that, we'll just do var web client equals new web client. We're doing nothing new here that you haven't done. This is not asynchronous. This is showing how it was originally done. So we'd have a result equals the web client.download string. And then we pass in the URL. And then we can log out we could log out the result, but to be honest, I don't think we want to log out the whole result. We'll just log out some of it. So we'll log downloaded URL, and then we'll just output result.substring. We'll always presume for this example that we have 10 characters, say. I'm not really bothered about this example not crashing. It's, we shouldn't not crash here. So let's first make use of this web download string. So we will have here, I guess, what shall we call this? a sync versus async method. And we'll do web download string. And we'll do our website equals google.co.uk. And we'll pass in website to fetch, download the string. And let's just run that for now and see. That should happen and download and output. What we're hoping is 10 characters. So there we go. We can see it's got some file. That's all we really care about. It's got a string. You can inspect it if you want to see the whole string. You can just put a breakpoint there and inspect. It's, you know, up to you. We should also, just for quickness in this example, let's also do private members. The event finished callback for the thread event example. Now I'm going to do some settings. So private static boolean run thread examples. And this is just for quickness. So now I can jump into each of these and wrap it to say, you know, and to be honest, I could kind of wrap the entire thing, save doing it inside each of these threads, but it's going to make all the comments out of line and start indenting. So for the extra bit of work, I'm just going to do it for each one. So run thread examples. I'm going to go to there, copy that bit, then just go to the bottom and indent. And then I'm going to do that for each one. So just bear with me while I quickly do that. And it just means that we don't have to sit and wait for all of these examples to run as we're working through this. We don't want to wait for, you know, 5 seconds every time I run something to see finally when we get to the examples we're talking about. And then you can just turn them all on as and when you want to run them, and it's nice and clean. There we go. So now if we run this, we should get straight into our example here, which is downloading Google. So we've also got to put in the logs that we do to keep things the same. So before sync versus async thread, or rather before sync thread, because then we'll do one before the async one. And then again, you'll see the results here. So that's no different than running anything synchronously. So now there's the asynchronous call, which will finally make use of the async and await words. So we'll do private static. We'll also do a void right now. We're not going to bother returning anything. I'll show you the actual physical task after this. I just wanted to show you the actual code example. So to be honest, we can almost copy all of that, and we'll start with that to show you the changes because there's very few changes. We can also even copy the comment and paste that into there. Because like I said, there's only about a line of difference. So this will be web download string, and we'll call it async because that's the typical naming convention for anything asynchronous is to end the actual name in async. Now the only difference we do is we tag before the return type. Typically we tag the function with async. So this is the keyword here, async, and now you can see it's going to tell us the async lacks an await operator because they run, you know, they expect an await. And the await comes when we change this download string function call to a download string async, which has already been made for us in the library. And this overload simply has to have a URI instead of just a string, which is a minor change. And then the result is, in fact, what am I doing different here? So the task async is what they do. They've got two of them. One's asynchronous in the old style, which we're not bothered about. And and this is the correct one. So download string task async is the name we want. And now you can see if you hover over, it's a task, which is the first time we'll have seen the task here. And it also says in brackets awaitable. So that's a hint that we can await it. So at the start of it, if we didn't await, the result's a task, which is not what we want. We don't want to get into tasks just yet. Instead, we await the result, and now the result's back to being simply a string. So the key differences here is really we've put async here, and we've awaited a call that now returns a task of string instead of just a string. And they're the only two differences. So again, this is the whole point of the async and task library, if you will, in .NET now. It's meant to be as little work as possible and as little change to your code, so that when you look at this, you can naturally understand it in the same way. That code comes in here, goes to here, runs this. This now runs on a new thread, but effectively you get to here after that fact. So you're doing what all of these examples were trying to do. You're trying to run something on a new thread here that then carries on here. And we can prove that by stepping through line by line. So if we just also copy and paste the before async thread, after async thread, and we do the async call, and we run this, we'll see that we have before sync, and then here we now step through, which will have hit. We're mainly bothered about this, so we hit this, spins off, and then the next line's here. So we've even stepped through just like it's synchronous code. We haven't magically disappeared off somewhere and come back. We have, because if you look at the call stack, you can see we're not, this wasn't the previous line of code. So the magic's happened for us, but in terms of what we've visually seen and what we've stepped through and what we've understood, we've gone line by line. But what it did is actually a lot more complicated, and we'll go through that after. But in terms of understanding what happened, and then appearance-wise, it looks like it all happened exactly the same. So we have here the exact same behavior. So before, download, after. And then here you'll also notice we've now got before, after, download, because that's the point of asynchronous. It's happening without waiting. So we're back to now happening and not waiting. I think I'll just also put a break between those two lines just to separate them. But I don't think they need to be in their own little container. That will also, we don't know how long that'll take, so we kind of can't await that. We can await it, but it's not necessarily going to be accurate if we leave it as this. So one other thing I will do is change this void now to a task, so you can see. And nothing changes, you'll notice. So I changed the return type to a task, and by default it's returning a task. And you might wonder how that is. And that is because this await effectively returns. So when you hit an await, it's actually returning the task at this point. And then all magic happens after that, which we'll explain. So just think of a task as if you await it, or if you await anywhere inside the method when you've got a task, an async task, then you don't need to return, because the await itself is the return. I know it's a complicated thing to try and understand, but you're not actually having to say return something, because a task is like a void. It's an asynchronous void almost, you can think of it as. And as we mentioned in the comments here, a task encapsulates a promise of an operation to complete in the future, which makes sense because we're returning at this point the task, and the task is the promise that this code's run first, and we've returned a task, and the task is the promise that this will happen after, or rather this will happen after this bit of code is run. So that's kind of what's happening with that, but I just wanted to add that so I could then show you here. We can now also await, but we can't await directly in here because we are in static void main, so we have no way to await that as such. So I can do something that I wouldn't recommend doing this specifically, but it's okay for this example, and we'll talk about it after. Download the string asynchronously and wait just for example. Or rather, if we do, and the only reason I'm waiting is to show, so whatever we do after this line always runs after that's finished. So var download task equals that, log after, and then here now we want to wait for task to complete, download task.wait. And now we'll be assured that that dashed line will always happen after the download. So even though that's happened and then this has happened after, we've waited on the task to complete. So that's kind of the starter there. So this is your first introduction into async and await and task here. This is how the typical functions look. And I want to go obviously more into depth about that. And a few key things, as I've mentioned, as one, if you see async, you should, it's not going to break if you don't do that. If you do this and comment out this, invalid code, it's not going to compile and say you can't do it, but it is going to warn that saying there's no await operator, so it's going to run synchronously. So in theory, when you see async, you should always see await. The other way around, though, you cannot await if you don't see async. You have to have those two in pair. So these two you can almost think as a pair. The async is a method value. Doesn't go into the method signature, meaning that if you were to override this function, you don't override with async. Async's a compile time directive that changes the physical method. But for what you need to worry about, if you see async in the method, you should see await in the actual method body. And 100% if you see await here, you will see async in the method. So those come as a pair is kind of the point there. And it goes the same for lambda expressions when you create them dynamically. If you were to do var a equals, you could do async and create a dynamic function and await, something here. And you can create a function that way. And you can't explicitly type it. You'd have to tell it it's just a task, say. Cannot convert lambda task because it's, well, whatever the case. The point is that, when you're defining them in a function, you can simply, instead of defining it like this as a lambda, you can put async in front of it, and now your method inside is asynchronous, basically. So you always see them, in a pair like this. And then the next point, which we'll put these in the comments first as we go. So we've kind of shown that, and I want to, finish off the comments. So async and await are always used together. A method or lambda is tagged with async. A method or lambda is tagged with async, and then any task can use async to asynchronously await it. So that's kind of what we're trying to state. So method or lambda tagged with async. Let's write this a bit better. And then await any task. That's really what we're saying. There we go. So that's the basic statement there. So the next thing is when you await something, and this is where I'll kind of explain what happens, then we'll go into an analogy, and then I'll deep dive into what's really happening. So when you await something, in terms of like here, the thread which called the await, which is this thread, the thread that we've come in on, a thread that called the await is free to return, because as I mentioned, the function does actually return here. And when it compiles, it does change, and this function really does say return task, and it returns the task from here. And all, magic stuff happens that we'll explain. But basically, the calling, the task that called this, called the await, if you will, it's free to return and do what it wants to do. And then in parallel, this function, the task inside, if you will, the await, so effectively this method here, whatever it is that comes after the await on the right side, now runs on another thread. And once the task is done, it returns to here to start some new work, or rather it returns to this line. It sets the value to here. So the left operator here, technically it returns here and then carries on below. And where it carries on all depends on the context and, well, really it depends on the context and the partitioner, if you will, of tasks, which won't mean anything to you right now. But ultimately what happens is you come in on, say, thread 1 here, and you get up to this point. and then you get returned a task. And now thread 1 carries on, as we've seen, does whatever it needs to do, which, if it's just a thread with no context, it basically has no other job, so it kind of waits there anyway. Nothing really happens. And this then runs on a new thread, this action, and then when it returns here, you'll notice this will end up being on a different thread. So if we actually paid attention there, what we should see is, you notice in fact, have we not awaited that yet? Oh, sorry, we didn't await it, so it hasn't changed the flow. So if we were to slightly change this and say, let's make one more example, because there's a key difference between waiting and awaiting, because waiting is a synchronous operation. So this time, before async await thread. So now here, if we properly await it, so we want to wait for that task to finish, which we can't because we're on a different thread. So we'll have to just do new thread, or rather task we might as well use. Start using them to show you, and I'll explain this one after. We spin up on a new thread just so we can do this. Task.run. Why are we not getting... and maybe it's just compile time error. Give me a second. Await before async await, after async await. We don't need to wait now because we've awaited. So that's the same there, but now, why have I not got... There we go. So now we'll just wait this task. So what I'm doing here, in order to await, because we're in a console app and it's a single threaded, well, it's not a single threaded app actually, because we've got a single thread here, though, static void main, we can't put async here. It doesn't let us do that. I think it does in future if you update to the latest one. In fact, yeah. Oh, is it letting us do it now? C# updated that to allow it. In which case that makes my life easier, but I don't think it does. Let me compile first and check. Yeah, I think it's going to complain that there's no entry point into the application, but it's not showing the error for some reason. But yeah, you can't have a static void main with async. So what we're having to do is to spin up a new task, or rather a new thread in essence, and make it asynchronous. So this is where I was talking about you can make an async method here, a lambda expression. So we spin up a new task and we wait it. You don't need to understand this just yet because we'll explain it in a minute. But all that, this wrapper here, the task and the wait, is simply so that I can do an async inside and show a principle I'm trying to explain. So let me run this and then explain what's happened and what's different. So you've got your normal one, your synchronous, that we know how happens. You've got your async one, the first true one, which goes start, finish, and then this happens separately. And now you've got this, and this is where you really use async. This is how you typically use it. You do something, you'd await a function, you do something else. And this happens, then this happens, then this happens. And that's what's happening inside the function here. You're doing that, then you're awaiting that, then this happens. But I can't show the principle of changing thread because this is a function we haven't written. So nothing, we can't go into that and say, let me know what thread you're running on. Can't log anything out. So all I've done to show this principle is just spin up on a new thread, and then we output the thread we start on, we await some work that outputs the thread it works on, and then we see what's after. So what that gives us is, before async await, we're on thread 8 now, because we've spun up a different thread here to do the work, but that's not important. What's important is the original thread. So you can see before we start the work, we're on thread 8. Then we call this call here, web download, and it jumps onto thread 5, which you'll also notice has already been used above. The thread's been reused because I've made use of a task here. So the tasks make use of a thread pool. So the key difference is we start on one thread, then we say await this work, and the work happens on a different thread. But you'll notice even though right here, the line after and the line before, we're on a different thread. We've actually changed threads. And that's an important thing in the await. And it's similar to the reason why the event-based wait method changes thread, because the thing firing back and coming back onto to do the work is the thing that's on the new thread. So we've said await this work. This work goes, right, I've been told to await, so this bit's going to happen on a new thread. But then when it has to come back and continue afterwards, because remember the function returned here, it has to continue the work afterwards. It's got no way to get back onto the original thread unless there's a synchronization context to jump back on. So what's happening is we're on 3 different threads, and you can see that happening again in the debugger. If we breakpoint it, and you'll see here we've got code, we're in an asynchronous method, and we're on, we do debug window threads. You can see right now we're on thread 8, and it's a worker thread, and then we step over that, and you see all of a sudden now we're on thread 5. Thread 8's down here, it's not available, and we've got thread 5. Thread 1 is waiting for the task here, so on one thread, it's waiting for this thread to finish what it's doing, but you'll see effectively the thread's changed, and also the call stack's changed to this resume, so we know something is going on here. We know some magic is going on, and that's what you need to understand about tasks is, even though it looks like you've done 1 thing, 2 things, 3 things, and you're debugging it goes 1, 2, 3, there's a lot of things that really happen in the background that you should understand. So to explain a task, it's nice and simple. It's you do work, and if you chuck await in there, the thing you're awaiting does its work on a separate thread, and then calls back and starts working here again. But the key thing you need to understand is what's happening in terms of the threads. So let me just put this note in the code as always, to keep this document up to date. So I'll just chuck my notes in. So when you await something, the thread which is called the await is free to return and do what it was doing, which we know. While in parallel, the task inside the await will now run on another thread, which we've just explained. Once the task is done, it returns to either the original calling thread or carries on the thread it was on to do the work. It returns to the calling thread or carries on, and that should really be another thread, because it's not specifically always that thread. So this is kind of explaining what I've just explained. It's just a sentence to explain what I've just been speaking about. So that's kind of another section done, if you will. That's describing what a task is and seeing the task and the async and the await in action. So now, because this is probably starting to get confusing, we really need to give it kind of an analogy. So we'll move on to the async analogy. So let's just copy and paste a header, and we'll say async analogy. And this is now a way to try and explain, I guess, what async is in terms of, say, a real-world example. So considering I like coffee, let's imagine you go to Starbucks, and the entire shop is run by one person, and is inventively named Mr. UI Thread. So you walk in and you ask Mr. Thread for a vanilla latte, and he obliges and starts to make you a coffee. So he puts the milk in the container, turns on the hot steam, and basically proceeds to stand there while the steam warms up the milk and tries to get it to 70 degrees. So during this time, you basically realise that you want something to eat, you're quite hungry. So, oh, I'll have a muffin. So you shout over to Mr. Thread and you say, can I have a muffin, please? And he just ignores you because he's basically blocked. He's waiting for the milk to boil. So his thread is blocked. And this is the analogy of the blocking thread. It's one thread doing one task, and while that task is happening, the milk's boiling, the thread has to wait for the milk to boil before it can proceed to do anything else. So several minutes go by, 3 more customers come in, and they're all starting to queue up and they're waiting to be served. And then finally, when the milk's finished and he's ground the coffee and made your latte, he returns to you. And naturally, you'd be a little bit annoyed. You've just been ignored for 3 to 5 minutes while you asked for a muffin. He didn't turn around. He didn't acknowledge you at all. It was like he didn't even know you were there, which he wouldn't do because he was blocked waiting for the milk to boil. So you decide to leave the muffin, get your drink, and go and sit down. And then he continues to serve the next customer one at a time, doing the same job over and over. And obviously that's not a good situation. So this is what's happened in single-threaded applications, and this is what does happen. This is what the UI thread does. There's only a single thread that can serve the UI. And this is the reason why, if you do any intensive work on the UI thread directly, your entire UI, your buttons don't respond, your animations don't respond, you can't move the window. And that's the same analogy as, the owner of Starbucks is busy standing waiting for milk to be served, just like your application might be waiting for a site to download a file. So this is kind of the analogy of a single-threaded business, a single-threaded application. So in order to improve the business, Mr. Thread decides to employ 2 new members of staff called Mrs. and Mr. Worker Thread. And the pair work independently. And as Mr. Thread takes orders from the customers, he asks Mrs. Worker Thread to complete the order. And then without waiting for Mrs. Worker Thread to finish the drink, proceeds to serve the next customer. So once Mrs. Worker Thread has finished the drink, instead of having to take her drinks to the customers, she asks Mr. Worker Thread to serve the drinks. And then without waiting, she proceeds to start the next order. So this is an example of a 3-threaded system, a 3-threaded application. So basically what happens is the owner, Mr. UI Thread, can happily take orders from customers. And then once they come in and need to be made, he asks Mrs. Worker Thread, so thread number 2, to go and make that drink. And then Mr. Worker Thread is thread number 3, and his job is that once the drinks are made, he goes and takes them to the table and comes back. So that all 3 work independently, and all 3 have callbacks, if you will, or they can resume to each other and give each other tasks of what to do, so that nobody's held up waiting for somebody else. And this is kind of a loose relationship between general multi-threaded applications, and that's what we're trying to achieve, is this work happening asynchronously. So hopefully that little kind of analogy gives you some thought pattern into what happens when one thread's doing all the work versus when we're splitting off onto these second threads and those works are happening independently. So I don't know whether that was any use, but that's kind of an analogy I've come up with. So I'll just put this analogy in here. And basically the key point here to notice when we're explaining this, and the key thing at the very top of this example is what asynchronous is. And it's to start something and you don't wait while it's happening. And if we kind of read the example I've just explained, then you've got like a key line here. Then without waiting for the worker thread to finish the drink, proceed to serve the next customer. So this in itself is kind of the nod towards why something's asynchronous, because things are happening alongside each other in parallel. So hopefully that's some analogy explained of what should be going on with async. It's also got you a basic example of a task and how to use them, which, to be honest, using tasks is not a complicated thing, as we mentioned. All you have to do is return a task, and then in your task you're free to await, and ultimately that just allows you to then do whatever you want asynchronously, which ultimately boils down to being a task at the end of the day. So now we'll really move on to the digging deep into what actually happens with a task, so you understand the inner workings. So we'll start with showing what happens in the synchronous part of a task. So this is also an important thing to see. So we have all that there, right? And so this will be the synchronous in tasks, or the synchronous part in tasks, because some of you may know this. I'm guessing if you're watching this video that you don't. But tasks, and in terms of, say, anywhere you see an async, or it's returning a task. So this is now a task function, if you will. This code, some of it actually runs just like a traditional synchronous call, like this call. And I hinted to it in the last explanation, that when you call into this, that this part of the call up until the first await is actually run in the same thread. Doesn't actually turn, that's the wrong comment there. Doesn't actually turn asynchronous until it hits this await. So up until that point, it's a synchronous call. And ultimately, when it's compiled, it's still a synchronous call. It never changes because this gets changed anyway. But that's, in terms of looking at it, this is an asynchronous method. But an important thing is to be aware of what's happening in what thread. As I say, that's the only real importance that you need to know about tasks, is be aware of what thread you're on, so you understand the importance of what thread you're going to lock up and what's going to happen when you return. So let's just do another example first. Let's just make a private static task, and we'll call it do work. And it won't do anything specific. All we'll do is say we will log doing work for, and again the importance is string for who does some work asynchronously for somebody who we are doing the work for. And the only point in this is to show what threads happen when. So we have, well, I guess this is also showing you how to actually make an asynchronous method. Done work for. So this is just going to log that we're doing work for somebody and then we've done it. We'll make it an asynchronous task so we can actually do it, and it should, as convention states, we should name it async at the end of it. So do work async is now the name of the function. And then the work itself, we want to do an asynchronous work, but we also want to log what's happening. As we mentioned, that's what we can't do here. So the simplest way to now make an asynchronous method, if you will, we'll just do it dynamically, and we'll await it though. So we'll await, and we'll just do a task.run. And a task.run allows you to basically put inside here a method or a delegate. So just, your normal Lambda expression to make a method to run. Now we can type whatever code we want in here, and it's going to run on a separate thread to this. So that's all there is to making something asynchronous. Well, it's the simplest way. So now in here we can say doing work on inner thread for such and such. And then in here we'll just simply await task.delay. And we'll just wait for the typical half a second. So this will be log it, start a new task, so it runs on a new thread, or rather, different thread is the key here. It doesn't necessarily mean it's new because task uses a thread pool which might pick a existing thread. And then, as mentioned, in order to await something, we can put async into the inner method that we're calling. So this then turns into a method that wants a task, and now the task is returned here. So we have a delay. And then finally, an important thing to explain in a minute will be once we're done working on the inner thread, because you'll also notice a surprise here. So all this call is going to do is it's going to come into here, it's going to log the thread, it's going to start up asynchronous work, which means it'll spin up on a different thread. So we know this thread will now be different from this thread. It'll then do something, which doesn't matter, this is just fake work to do nothing. And then we'll also log once we've done that work, and then finally when we're here, which should be after both of these calls because we've awaited it, and then we'll return to the caller. But what you'll notice is this will help us explain what happens and where. And you could always step through the code, but now we've got the logs, we don't need to step through, we can run it and then explain it. So we will call do work async, and again we need to await a task.run just because we're not on or rather we can't await the task.run, can we? Just do task.run .wait, which should compile. I think it's just complaining. What's it complain about? Do work async. There we go. So this will be for me. It doesn't really matter. So run some work to show the threads or the synchronous parts of the call. So let's just run this and then I'll explain what's happened where. So we'll have the classic downloads I'm not bothered about for now. So now we get into here. So in fact, we've forgot an important step. That's to actually log anything out here. Kind of the whole point of what I'm trying to show. So we've done the work. We'll log it like everything else. And then what do we typically do? We say before submit thread, after submit thread. So before do work thread, and then after do work thread. So let's see what happens here. So if the downloads happen, right, so here, we come into this, which we know now what happens. We do a task.run, which spins up a new thread, and then we synchronously wait it simply to bring it back into the console, thread. So that's not important for what we're doing. This bit's then the important bit. So we start work on the before thread, which is thread 8. And now we say, do some work. But what you'll notice is this is asynchronous. We're saying to do this on another thread. So everything inside this function you'd think is now on a new thread, which means do work for me should be on a new thread. But you'll notice do work for me is on the same thread as the caller, which actually means we're holding up the thread. So even though it looks like we've said async and that this now work you'd expect to start up on a new thread, the important thing here is it doesn't actually do that. It's locking the thread at the point of up until the point of the await. And something else we can do to show that as well, which we'll show separately in a minute, is to do, let's first get that task. So we'll just say var do work task equals the task. And if we don't await it, you'll notice we get a task back. So as I mentioned, what do you think would happen here if we do this? Let's run it and see. So we haven't awaited the call. So what's going to happen? So firstly, you'll see before do work. Then you'll see doing work for me is on thread 5 still. And then after work is on thread 5. And now inside here, doing work on another thread's carried on and all the rest we don't care about right now. But the important thing here is you'll see that we've done before do work thread, doing work for me, and after work. So even though we haven't awaited, what's happened is it's still run the code up to a certain point. And that point is the first await. And it must do that in order to do what we said, and that's to return a task of a promise for work to be done later. So in order to return a task, it must hit the point at which it's awaiting a task. So what happens when you call this function and you don't await it is, or even if you do await it, the same thing happens. It just changes the flow upwards. But the way we've just called the method is it comes into here, just like a normal method. It hits this, it hits the log, and then at this point, it returns. So it returns here. And then, even though we haven't stated return, this is effectively done, return task.run. For in essence, we've returned the task. So we've actually ran this line of code directly in the same thread as we were in. So if we put a breakpoint on this, you can see it happening, and you can see the call stack doesn't change. So we're on here, we're on thread 1, I believe. Yeah. And then, in fact, are we? Never been on thread 1 before. We're on thread 5. Why is my thread window not right? Anyway, oops, let's run that again. Put a breakpoint before if I can. So we hit here. There we go. For some reason I needed to step over once to show. So we're on thread 8, are we now? Yes, there we go. So before do work thread, we're on thread 8. Now here, if we press F11, you'll see I'm still on thread 8. And I'm also, importantly, I can step back up the call stack. I'm still here. I'm still in this code. So right now, this is running like a normal function. So I'm on the same thread. I haven't changed threads. I'm still on the same call stack. Nothing's changed. I'm still exactly where I was. I'm inside this function running in the same thread. So this is nothing asynchronous right now. But importantly, at this point, you step over, and unfortunately the step overs kind of showed that to happen. We wanted to have a breakpoint here, so let's just do that once more. So we step in, we go through, we get to here, and then as I press this, you'll see it's come back here. So we've actually returned a task, and then we've got the code here that's still, running line by line. So the point of what I'm trying to explain here is that, let's comment this. So we will say do work. This will return a task and run the lines of code inside the method up until the point at which the first await is hit. And this is important because, say this was your UI thread and you're in WPF, and we'll get there, we'll make a WPF app. And let's make the presumption that you were awaiting this. So I've split it up just for simplicity. And then you can do await, do work, task. You can, do the await afterwards, doesn't matter. You're awaiting a task. But I wanted to show that at this point, work still happens and the await happens here. That's no different than doing await, that. But then you can't see the split of what's actually happening, the steps in between, which is one, it does return a task and you can get the task, and then it awaits it. It just inlines these two actions. So by getting a task back and then awaiting it, it's just a shorthand of, or rather this is the shorthand to simply await it in the first place. But by doing it this way, you can see that this line runs just like a synchronous method. So everything before the first await here is run on the same thread synchronously. So if this was a UI thread and a button was clicked, and in here you had some huge amount of work that did thread.sleep 10,000, say, and we didn't await the function, which we haven't. So if we don't await the function and we get to here, we'd expect to get to here next. Then what you'll find is that you'll hit here, we should step over, and it hangs for 10 seconds and then gets to the next step. So you can see it's running on that thread. So if that was your UI thread right now, work that was done asynchronously, if you were to do what is natural to appear like fully asynchronous, which is this, if you were to do that, then you'd find that even though you'd expect this to run on a new thread, so there you go, and you should hit here right after, it doesn't. It's locking the thread. So it's a very important piece of information to be aware of, that when you see async, it does not mean that the code inside is necessarily running on a different thread. It only changes thread at the point of the first await. And if this await gets hit, it goes then into this function called this await. So it'll still run this up until the point of the first await, basically, is the the important piece of info. And then the bit that awaits, basically, this will then spin off to a new thread and come back with the result. So at that point, if we then run the function and look at the output, we can see what happens in terms of the threads. So we have the work thread, which is 8. Then we know that when we go into there and create it, it does this bit for us on the same thread. So it says doing work for 8. It hits the await, so it returns. So we get up to here now. And then we've awaited the task. So at that point, this says, right, hold up, free up my thread, but go and do your work on another thread. So then the inner work, these two lines, spin up a thread to do 4. And the important thing here, as I mentioned, this happens all the time. So even though we're in an asynchronous call here, and we're now on our own thread and we've done log, when we await again, every single await does the same thing. So the await now is going to go into here and say, well, this wants to happen on its own thread. So awaiting a task that awaits a task has actually spun up another thread. So we're now, this line of code's on thread 4, this one's on thread 5, because the callback happens that way. So if we were to repeat this, multiple times and run this code, then what you'll see is each time it's changing thread. I mean, it's reusing threads because of the, the fact that the previous threads have been freed up. But the important thing is, every time you're coming after an await, the thread's changing. So that's something to bear in mind, especially on UI threads, that what happens with, the threads when you're awaiting things. So I'll just put all this into the notes to keep them up to date. So the synchronous part, well, to be honest, there's no notes to be made. I've kind of made them in the comments. So this is the synchronous part. So I'll just wrap this in a region. The synchronous part of tasks. And then end region there. And then you might just want to get a coffee or have a break, because this is quite a long video, and refresh your mind, and then, come back to here as we move on to, the other bits. We've still got quite a bit to go to really explain tasks. So the next thing I will do is explain return types. So we'll do async return types. This is fairly simple. It's not as complicated as the rest. So for an asynchronous task, as we've seen, we can return void. We can return task, which are both awaitable operation. Well, rather, the task's awaitable, the void isn't, but it returns nothing. So in terms of wanting to do some work that returns a value, then if we copy and pasted the whole thing, do work and get result, then if we want to get some info back, then we would change the task to a generic type of task with the return value. So let's say we want to return a string. And now it's going to complain that we're not returning a string. So you can return a void, you can return a task, or you can return a task that actually does return a value, which means that you simply await for a result. So if there was a call that was going to return something, then that's where the await returns a value. And that's what happens in here. So this download string is actually a task of string like we're doing now. So I'll show you how to do that. And that's no different than thinking of like this method, a task with a string. If it wasn't asynchronous, you'd remove async, you'd remove task, and you'd remove the brackets. And this is what you're looking at. It's just a private static function that returns a string. So all we've done is wrapped it in a task and put async in. But ultimately, it's just, you can ignore async task. That just means it's asynchronous. The ultimate thing is we're returning a string. So in here, because we've already awaited a task, we've done something, we can now return just a string. And we'll just return the value they passed in to us. Return what we received. So now, if we were to call that method, var do work result equals do work and get result, return this. That right now will obviously return a task, which is not what we want. We need the result. So we could do dot result, which is something you should almost never ever do. So there's very rarely ever a case that you want to directly access the result of a task, because this basically boils down to going right the way back up and becoming a blocking wait. So you don't ever really want to do result. What you can do is do a wait and then get the result from the task, which is slightly better, not massively, but slightly better. It doesn't block the thread entirely. But because we're on a synchronous thread here, the console app is running on this one thread and it's synchronous. We have to keep jumping off to tasks and then waiting them. So we could do that. We could do task.run and then do our work and then .wait afterwards, to await the work like we've done before. But I'll show you a slightly different way. Say if I'm going to spin up a new task. You could say var do work result task equals get the task, as we've seen. Get the task. Wait for it. So then we do var result do work results, or rather it'd just be do work result task.wait. Get the result, and it would be do work task.result at that point, because we know it's complete. That is the same as simply converting to as we've done in every other example, a task.run, and then we're waiting on it there. And then inside here now we're free to simply do var do work result equals do work and get result, return this. And that's typically how you'd see it written in a one-liner. This is the other way of doing it. So in hindsight, I'll simply comment that out, or rather I'd say do work result. Well, no, I'll comment it out because that's not, I'm just showing you a different way of doing it. You can get the task, you can wait it, and then you can get the result. That's if you're in a situation where you're in synchronous, and then the other way is to simply spin up a task and wait the task, and then get the result. So you've done it a bit safer way. So I'll comment that way out. Or in fact, I'll just delete that way to it. No, I'll leave it in. I just don't like commenting it out, to be honest. So let's just region it. And we'll say method 1 getting result of async from sync, because that's what we're doing. And then we'll copy that region. It's a long region name, but who cares? That's the other way. Do work result 2 is then get this. So if we run this and simply breakpoint here and run, we'll see all the other code running. Then we'll get to here, and ultimately we'd await in the next line, and then we now have the string. So that's all we've done. And then in terms of threads, you can see what's happening with threads. We also need to put some breaks here. Doing work, we haven't put any breaks in. But you can see the, yeah, it's not very clear. Let's clear that up. So we have synchronous part, after work done, we've waited. Let's just get a breaking line to chuck in there. That's the line separation. Then method 1 would want line separation, and method 2. And there we go. In fact, still want something different. We need to change. Oh no, we don't. Return this too. Yeah, that's fine. So now I can see the last call we did, which was this result here. We doing work for return this 4, which will be the thread we've got here, which we haven't logged. In a thread, as we've mentioned, jumps onto separate ones and comes back onto a different thread returning. But you've seen all that in the previous examples. The point here was to mainly show you the return types, how to get a result from an asynchronous call. So now we've made a call that returns a string that simply, does whatever it needs to await whatever it's doing in its own code that's asynchronous, and then returns a value. So that's really all there is to the return types. There's void, which can't be awaited. There's a task which can simply be awaited, but it's like a void action. It's like, a void method. It does nothing, but it's an asynchronous void, if you will. And then there's finally the task with a return type, which is just like any other method that returns a type. So I'll chuck these notes in about the return type. So you can only return void task for a method marked async, as a method is not complete. When it returns, so that no other result is valid, which basically means, as I mentioned, the method does actually return at the first await. So the only thing it could possibly return is a task, which is a promise of something to be completed in the future. So there's nothing else it could return because it needs to have a promise of doing this work afterwards. So that's why it's the only valid sort of answer. So that's that one wrapped up. We are up to return types. So the async keyword we'll mention next. So as I mentioned earlier briefly, and a hint of it was, the async keyword, when you see here, in all your functions, it's not actually added to the method declaration signature. And by that I mean, if we were to say make an interface, so we were to do public interface something, and you were to define an interface, and you do like void test, and it's a function, you couldn't add async to it, because async is not actually a signature, and you'll see it complains. The modifier async is not valid. It doesn't really tell you why, but the reason why is the only effect async has on a signature on a method declaration here. The only effect this has is to change the compiled code. So it tells the compiler that inside your code, wherever it sees an await, is to completely change the structure of your code. So it does something very similar to the event callback style code. So let's take the simple example of this one, and let's pretend we were going to compile the code and tweak it. So if this saw the async here, and you now compiled the code, what would happen is it would say, oh, there's an async here. So first thing it does is remove the async. That doesn't exist now. At this point, it then returns the task. But before returning the task, what it does is it stores all parameters, as in these here, local variables. So if we declared any variables here, it would store those. All the contexts to do with the calling context, the synchronization context, execution context, security context, everything to do with the thread and effectively the context at which this code is running in. And then it would also store this variables, which means the class in which this code is running, because you could have local class variables like these private ones here. So at the point of hitting an await, it first then, and it physically writes this code, so it compiles and outputs code. So here it would then store all of those variables. Then it would start a new thread, or rather it would ask the thread pool to start a new thread, and then to run this bit of code. So it would almost convert it to, and again, not in any way directly like this, it would say, oh, there's a new thread, go ahead and do this work that the guys asked for. And let's pretend that just wasn't in there because that's just looping. And then after it started the new thread, it would then now return a task, which is a new task of whatever it wants, with a promise of the work to be done. And again, it boils down, you can't write it because it's not the code that's available to simply write, but it does store all the variables, starts a new thread off, or starts the work off on the thread pool to go ahead and do that work, and then it returns a task that it's expecting, and this inner task will now be hooked into this thread, and at the bottom of the thread when it's finished, it would then do a callback, and this callback is part of the thread, which would then say, right, now I've got access to all these contexts, and what I'm going to do is make use of the context to try and find out where I should do my work, the synchronization context. Otherwise, I'm just going to start up another thread and call back the code, and this bit here after the await becomes the callback. So as well as storing that, it would then say do for callback equals, and it would make a new callback method from that code, and it would say whatever, like say this isn't a compiled code, but then it would call the callback, in similar terms as that. So it's kind of what we did with our event-based callback. But all that's kind of, that's fake code I'm trying to show you. But what actually happens is this async does do a similar thing, a lot more complicated and a lot more structured. But in essence, it physically alters your method call. And in another video, I'll actually install .NET Reflector and show you that physical change in code. But for an intro to tasks, I don't think we need to go, that deep. But it is important to know what the async word does. It does actually change the physical compiled code. And the key point is it actually does, your method really does return at this point to the first await. This code doesn't actually happen then. All this afterwards is not part of this code anymore. But the point of tasks is that it makes it look like it is. It's a nice, easy way to visualize that you're awaiting code, then something else is happening, without having to worry about making the threads and jumping back onto the right threads and things like that. So that's what that is. Just paste my code as always, and put the notes. And hopefully this all, it makes sense that you're getting knowledge that you really do need to understand tasks. As like I say, explaining tasks, I could do in 5 minutes, and that would be, here, the first way of doing a task. And then the second way of doing a task can return the result. And I could say, there you go, that's how you use tasks. But the most important thing in tasks is really to just understand what's going on with the threads more so than, anything else. So one little topic that really I've kind of covered anyway, as we've been doing this, but I'll do specifically, is consuming async methods. And typically, you can do this in most places. The best way to consume an async method, so let's say I would do work, and by consume, I mean effectively, call the work. So what's the best way to consume this, to run this code? And you call it, and it's obviously going to complain. It's going to be run synchronously. So that's not really consuming it in the right way. The best way to consume an async method is to become asynchronous yourself. That's by far the best way. So you typically go async task, and then you can happily consume the method as an awaitable, and now you've successfully consumed the method. So that's the first thing. The best way by far is if you can be asynchronous, be asynchronous. And that leads to a natural event with async, I guess, and async is classed as contagious for that reason, that when you get an async function, your natural thing is, oh, I've got to await it. It's kind of almost forced upon you, and you should. You want to drive that asynchronous behavior. And in fact, when Silverlight was around and popular, the only option you had in Silverlight was to be asynchronous, because the Microsoft team drove it that hard that they forced asynchronous everywhere throughout the whole framework. So you had no choice. So the first thing is, the best way to consume them is to be asynchronous yourself. If you can't, then please do not do this. Do not just get a task and do .result. This one doesn't return any work, but say you're getting, value. Don't do .result, because what happens there is this is a complete and utter blocking call. This will do nothing more in the most part as your blocking wait call. It will completely lock up your entire thing and destroy the whole point of the asynchronous behavior. You can also cause deadlocks this way. So don't do .result. There's a few options. If it's got a result itself, you can do .wait. But in terms of doing that, what you'd have to first do is to store the task. So that'll be var do work result task, which I think we've already mentioned above. So I'll just call this work result task. Some work or consume task, or just call it consume. So you store the task, wait for it, which is a better way of waiting. It doesn't deadlock your thread. It simply uses, I believe, probably ultimately in the underlying code, I think this will end up using a threading timer, which doesn't then hold up any threads. They're completely operational to do whatever they want. It's not a blocking call, so you won't get a deadlock. And then finally, now you can get the result. So that would be work result equals work result task dot result, which are now safe to get because the task is complete. Whereas if you try to access, even read the result before it's ready, it would block. So you shouldn't do dot result until you know the task is finished, and by waiting, you know it's finished, or it'll throw one or the other. So that's way one. So this would be consuming way, consuming one. I don't really know what to call this way. Consuming wait. I guess that's what we'll call it, consuming wait. Obviously, like I say, the first best way is to be asynchronous yourself. So another option is to be asynchronous. So we'll copy and paste that, consuming via task, which is really doing no more than what we've done here. Really, this is the ultimate way of doing it. This is really your answer. If you're forced to be synchronous, and the only option is to wait, that is the only option to get from asynchronous to synchronous. Really, you're best using the wait and then getting the result if you need it. The other option doing exactly the same thing is to simply, as we've seen many times here, is to just start up a new task. So task.run async. And I would personally use this method over the other, and then wait it. So that's what I would do myself. That's my personal preference. So that's consumed by task. And then if you want the result, you'd obviously declare the result. So for work result via task, then that would actually be your expected type. Or you could do var equals default string, a little bit nicer. And then this would be work result via task equals await. And you can cross the boundary like that. So even though this was created on one thread, it's set on another. Do be aware though, as we've mentioned and we've shown in this whole sort of video, is this is not going to be on the same thread as this. So if this is a UI element, you can't go ahead and just say button.text equals this here, because you're not on the same thread. But you should be aware of that now with what I've spoken about. You've got in your mind that this is thread number certain one, this is a second thread. Anything coming after this await here would be another thread compared to that thread, and so on. So get result. This is the other way I'd do it. And then before I forget, let's chuck the break line in there, and also the break line there. Let's just run and make sure this looks okay still. Keeps them all separate. Yeah, there we go. So you can see, as we mentioned, the different threads being involved. So that's how you would consume a task. Again, let me just dump my comment into here. The best way to consume or call a method is to return of a task is to be async yourself in the caller. That's ultimately to ultimately await it rather. And by that definition, async methods are naturally contagious, which is what I mentioned, and then some examples here. So that's consuming. So we're not too far off the end now of the basics of tasks. I'm sure there'll be more videos on the more complicated ones. So now we're going to talk about more specifically, I know I've briefed over it, but I want to really reiterate this point, because if you understand what happens in a task, you won't have any issue going forward in the future videos to further understand what's going on. So what happens during an async call? And you might say we've just spoken about that, but I want to be very systematic in this definition. So what I'm going to do is paste my very specific notes, and we'll talk through them one at a time so you can really get into your head exactly what's happening in enough detail that what you care about and what you need to know is in front of you. You can always read back and reference this document if you get confused. So, as we mentioned, code inside a function that returns a task, which is these, for example. So this code inside a function that returns a task, that's what we're talking about. And in fact, can we split the screen? There we go. Perfect. Right, so code inside a function that returns a task, this code, runs its code on the caller's thread up until the first line that the call awaits. So that means the thing that called this, do work async, our thread above, the work up until the async there happens on that exact same thread as if it wasn't in the function. It's not in any way asynchronous. At this point in time, once it's hit the first await, the current thread executing your code is released, meaning it's released in the sense that this function gets returned. So as we see, this actually does return, and that's why it's released. It can carry on because it's been returned. It physically has returned, even though you don't see it in code because it happens at compile time. So the current thread executing code is released, making your code asynchronous at that point because it's no longer waiting on the rest of the work to happen. So this means from a normal point of view, your function is returned, as we mentioned, and it's returned a task object, and that's why it's free, because now it's got the task, it carries on, and the task gets monitored and handled afterwards. Once the task you've awaited completes, your method should appear to continue from where it left off, as if it never returned from the method, so resumes on the line below the await. Or rather, if you're assigning something like result equals await, then it returns to the result section. But ultimately what that means is, once you go here and you hit the await, you'd expect this code to all happen, and then naturally below this would happen after. So what you're seeing is a sequential, almost synchronous appearance of code, which is the point of tasks. So you can look at this work log here now and see that this unit of work that you're trying to do in your head happens in a linear order, which is what you need in your head. It's easy to understand. It's how code works. You can think of it as this happens, then this happens, and this happens, and this happens, and this happens. That's exactly what does happen. In order to make that happen and to make it asynchronous, as we know, this unit of work must happen on a different thread in order for this to be asynchronous. But we don't really have to care so much about the fact that this has gone off on a different thread and the thread this is called from is allowed to free up. We're not overly concerned about that. But it's important to note that the point of the task is to allow that natural flow to happen and appear that it happens line after line. So to achieve this, and C# at the point of reaching the await call here, so right before this then delves in, as I mentioned, it stores all the local variables. So that means if we've got var boolean equals something here, that it'll store here. Stores the parameters of the call, stores the class variables, and it stores all the contexts, which I don't need to delve into, but things like security, if you're impersonating a user on the machine you're on, the execution context, the calling context, all the contexts of your thread are stored. And that's fairly, not massively, but that is consuming on the CPU and the memory to do that. And then on resuming, once it's stored all those and started all this, on resuming, so here afterwards, it basically restores all of those values as if nothing had happened, and that's the point of it. It makes it seamless. So if you were to put var, or rather say var I equals 68 here, and then afterwards down here you checked if I equals 68, it will. Because even though at that point in time it gets stashed away on the garbage heap, and then this runs, when it comes back and before this line executes, it restores those values for you, so that you have no real, recollection of anything changing. So that's what's happening on, during a call. So now we want to delve a bit deeper and go into what happens with threads during the call, which again we've briefed over, but we'll go very specific here, so you can understand what threads get called and when, and also start involving the UI thread. So let's just place that there and there, and then I'll chuck my notes into here now. So let's talk about the thread specific information about tasks now. So I know we're repeating ourselves a few times here, but like I say, it's important. So we'll start obviously reading from here now. So as you call a method that returns a task, as we've seen, and it uses async, inside the method, all of the code up to the first await runs like a normal function on the thread that called it. And that's what we've just mentioned in the statement above. But this is now focusing only on threads. So once it hits the await, we've seen above what happens, all the magic that goes involved. The function ultimately returns a task to the caller, and it does its work on the inside of the await. So that means it does the work here, this specific work. On the inside of the await on a new thread or an existing one. As we've seen, we get a new thread because it goes to the thread pool, which spins up one or uses an existing idle thread. Once it's done, so once that work's finished, and effectively after the await, so whatever line needs to happen next, which is here in this case, after the await, execution returns to a certain thread. So we know it's changing thread or potentially not changing thread, but it's returning the work on a thread. That thread's determined first by checking if the thread has a synchronization context, which we can also get if we do. In fact, I can put a little thing in here between the comments. For sync context equals synchronization context.current. And we will see if we breakpoint after the fact, whether we've got a synchronization context in this console application. So we'll see in here, we have none. So a console application doesn't have a synchronization context. So basically the thread is determined by first checking if we have a synchronization context, which we don't. If it does though, which it will do in a WPF application and most UI applications, then it asks the synchronization context for doing some work. And that would be sync context.post. And now it would post the method, if you will, that it's compiled, which would be this unit of work. So it would go ahead and at this point here at the start, it would create a unit of work that comes after, which is this. And then at the end of it, it would get the sync context and do post and tell it to do that work for us. So that's what's happening there. For UI threads that have a sync context, which we'll see, doing a post on the synchronization context will chuck the work to be run on the UI thread. So what that means is in a UI application, this unit of work here, after any await, if the work was started on the UI thread, any work after the UI thread will end up back on the same thread because of the synchronization context. So if we're on the UI thread here and then we await something, the beauty of it is that afterwards we're back on the same UI thread, which is a real benefit to asynchronous work on UI stuff. For normal threads, like this case, that have no synchronization context, the code after the await typically but not always continues on the same thread that the inner worker has been done on. So if we just run the code, you'll see that happening multiple times. So we'll see where we've got synchronous work, where we've got asynchronous work, you'll see here, work on some inner thread, thread 4. Work done after is thread 4. On the inner 8, after 8. On the consume wait 4, after 4. You can see that it's always typically continuing execution. So this runs on, say, thread 8. Then typically, if there's no sync context, this will also run on the same thread as this, kind of bubbles in. But it's not always the case. It's just a typical and very common case. So that's the normal case. If you use continue with instead of await, then the code inside continue with runs on a different thread than the inner task was run on. And again, that's a typical case. So if we were to do, say, do work async test dot continue with, we'll do test, or say continue with, and then in here we have the task that returns, and we can log that. So we'll do log continue with complete, and we were to do the same thing with an await. Well, we've done the await multiple times, so we don't need to show that. But we'll show a typical continue with here, say. Show continue with, typically changing thread IDs. And to show that, we'll also log a breakpoint as we've done all the time. The only difference here now is the continue with, hopefully is our last statement because it's not going to wait. Or can we wait there? Yeah, we can still wait there. So we can just do that. I don't think that'll change the behavior though. So we should get down to continue with, and we should see what we're talking about, the difference. So you can see there now, previously the inner thread, which was awaited, is on 8 and then continues work on 8. When we've done continue with instead, then even though the work's finished, do work for continue with 4, the continue with complete is now on a different thread altogether, 8. So they're just behaviors to be aware of that are very common and almost always the case, and I'll mention them here, but it's not a requirement. What is a definite though, is that if we are using UI and we start some async work on the UI thread, then the synchronization context is captured because we mention it here, it's captured. And when it comes to resume, it asks the synchronization context to, post the information back to the UI thread, which also means that anywhere in code, in a UI application, we no longer need the dispatcher we were talking about in the WPF applications, because you can use synchronization.current if you're on the UI thread, though, to post, back to the UI thread. So that means you can also store the synchronization context instead of the dispatcher if you want it to be a bit more cross-platform, because this is in system.threading. It's not in any way specific to UI, but that's another topic altogether. So for normal threads, we've read all that now. Where are we? So this also means after every await, the next line is typically on a new thread if there was no synchronization context, which is what we've also shown when we did multiple awaits. If we just pasted multiple awaits here, you saw that the thread changes every time because it's the same. Every time you go from one await into another, the same action's happening. So every time you go into await, this gets returned, this gets queued, this gets run, and then you hit this await, so then this gets run, this gets queued, and and the same principle. So each time, the logic of what thread we pick happens every single time an await hits, and that's why every single time the thread typically changes, which is not a concern to us. The only real concern you ever have with threads is, one, I just want you to understand the flow of it for a good reason, to make sure you're not locking threads and to make sure things are happening where you expect. But most importantly is you're typically working with UI, and in that case, the thread is very important and you have to be aware of which thread you're on. And then finally, there's an exception that if you use ConfigureAwait false, then the synchronization context is totally ignored, and it's resumed and treated like there was no context. So we can't show this until we start up a WPF application, which we'll do in a minute. And then resuming on the original thread via the sync context is an expensive thing, as we mentioned. So in order to make sure we get back on the same thread, all of the context and everything has to be stored, and then all the variables have to be resumed, and basically it takes time. It's an expensive process. So the only real time you'd want to use ConfigureAwait false is when, say, you're in a UI button click or something, and you've clicked a button, you've downloaded something, and you're awaiting it. And then the bit after here, when you finish downloading, you're not necessarily doing anything with the UI. So you're not setting UI up. Maybe you're just altering view models. In that case, you might want to do a ConfigureAwait false by just doing .ConfigureAwait false to say, now you don't care about this bit of code running on the same thread that the synchronization context wants you to. So it's more for efficiency. What you'll find most people end up using this for is to try and fix deadlocks in UI, which is a bad reason. If you're doing that, you're doing something wrong. So ConfigureAwait is not a solution to get around deadlocks. What it does is tell you that where you started the code, if you're in a synchronization context environment, which is typically UI, that the bit after the await, you don't care if it runs on the UI thread or not. So it saves the expense of having to restore all that information. So that's kind of the bit there. So I'll show basically the synchronization context and thread resuming section here about the the synchronization context. I'll kind of demo this point of the thread resuming on a very specific UI thread, which is different than what we're seeing now. In a minute, we'll just cover one more thing, which is exceptions. So just remember that, as we've seen here, we've got no sync context right now. So based on the example I've written, we go here. For normal threads that have no context, the code after the await typically, but not always, continues on the same thread as the inner worker, meaning not the one that started it, but it's no requirement to resume on a certain thread. So it means we started work on thread 1, and then we've resumed it on, when it was finished on thread 5. We started on 5, we resumed on 8, started on 1, resumed on 4. What you'll see in the UI thread is the work that starts on thread 1, which will be the UI thread, will always resume on thread 1. So it's a different behavior. And it's done for that reason. The synchronization context makes sure that awaiting is a natural behavior, that if you're expected to be on the UI thread here, and you await some work to be done, you'd naturally expect you to still be on the UI thread here. So that's the point of that. So I'm not going to go into any major detail about exceptions right now. We can always do another video on that. But what I do want to do is at least cover exceptions, so you can understand what's going on with them, basically what happens and what to think about it. So we'll say exceptions in async calls. And again, I'll just dump my notes in here. So we have some basic rules here. So any exception thrown that are not caught by the method itself, so right now all of our methods, are thrown into the task object. So this is specific, obviously, when you're in a method that returns a task. So if we were to create a private static async task, throw something, throws an exception inside a task, and we can do before the await. We can say throw before await because, as we mentioned, there's two key differences here. And then we can just do await task.delay. And to be honest, we don't care about any specific delay. And do throw new argument exception. Oops. So we've thrown, and then we've awaited, and that's just going to tell us it's unreachable code, which is fine. Just showing you as a point of what would happen if potentially it wouldn't throw. In fact, we could just do, we can just do a single call with a boolean before, and then we can just say if before, and then if not, we throw there. So we always throw if it's got past there either way. And then that would have parameter throws the exception before and await. So we have a basic function here, simply throws an error, nothing else. Let's start with the basic example of just calling that. So throw before await, and let's Control Alt and E and turn on exceptions, and obviously say before is true. So this should, in fact, we should also log a console. So log after throw before, which sounds confusing because now it's going to be before throw before. So maybe we do something like that so it looks a bit less confusing. So now we should never hit the after throw before because it should crash the thread. So what we should find is we get to there, we do all the work, this throws, and if we take a quick look at here, we've got before throw before, but then because we've crashed, and if we look at the thread we're on thread 1, the main thread, because that's where we've called from, it crashes, or rather it should have crashed the whole application. Interesting that it hasn't crashed the application. Is that just because throwing an exception is not, or am I talking about my own point here that's throwing on the main thread but allowing it to continue? Let's just check this out. So we throw there, and then it crashes. Yeah, so it acts different even though, and this is kind of the point of what I'm trying to explain here, even though it's running on the same thread, and this should in theory, in all rights, crash the application just like throwing here should, because that's what you're thinking. If you throw here, the application crashes, but if you throw inside here, even though that should perfectly crash the application, as we mentioned, async physically changes this code, so it's not exactly the same. So what's happening is it knows it's returning a task, and if you throw before, then instead of it just crashing the application because you expected to get a task back, then it's going to put that crash log, if you will, into the task. So if we do crash task equals task, and then if we log here and we like crash, what should happen is the exception gets put into the exception property of the task and it goes to as faulted. So this crashes, you're on the main thread, in theory you'd expect it to properly crash, yet it doesn't, it carries on the thread that apparently crashed. That's because the async word has compiled it so that it doesn't, it's got a try catch around it now. And instead the crash task now has the exception count of 1, and it should have it as faulted. It's got status of faulted, which I'm sure there's a property called isFaulted, which we'll check in a minute. But you can see importantly we've got the exception here and we've got the inner exception. So we know that the problem, we've effectively caught it. So one little quirk is that you'd think a throw before the await would crash, and instead it doesn't. So what we can do is var is faulted equals, and I'm sure crash task has as faulted. Yeah. Did it crash? Which it did. And this is just important to know and what to expect, expected behavior. The exception. We could do log crashed task.exception. And I think it should convert to string nicely, and we'll get a big dump out of the crash, which we can do. I don't think we really need to do that, to be honest. I can just do the message dot to string, so we just get oops written. But you'll see there's the crash, if you will. So that's not really important, but you can see the exception is there. So the exception message is easier to see. So that's this expected behavior that's different than what you would potentially think. So if you don't await the task, the exception will not throw on your calling thread, which is what we're doing here. We're not awaiting it, so it won't throw on the calling thread. So really, that should be kind of there. That bit is showing the throw on calling thread without awaiting. And then if you do await, the exception will be rethrown on the calling thread, so it'll crash as normal, even though it's called before the await. And we can't really show that here, to be honest. We'll have to do that in the UI application, because the problem with this is we can't await on this calling thread, because it's obviously not got an await that we can do. We're in a single thread, so we can't really await it and cause it to crash that way. But that's just a statement that, if you could do await here, then this would effectively crash this thread if it crashed before an await. So if there was thrown here, it would act just the same as if you'd thrown outside of the await. That's what it's about. That's what it's saying. So the exception to that rule is if the method with async has void, and that's because the magic happens by detecting that it's a task and it's got somewhere to put the exception. So it can say, hang on, this is crashed, but I wanted to return a task, so I'm going to chuck this exception in the task. If you've got void, there's nowhere for that exception to go, so it will crash just the same. So then we can kind of show the same behavior as what would have been in the other one. So throws an exception inside a void async. So this can just be exception void throw, and to be honest, we don't do before or after, or do we? Well, we don't really show it after. It's kind of, the point of it being after is that it would throw, well, let's leave that in just for an option. No point taking it out. So throw before await, throw before await void. Well, throw before, in fact, yeah, throw before await void is really the right way. Throws an exception inside of void async before awaiting. So, in fact, it's not before because we've got a boolean giving us the option. So that's throw await, and we say before. So now in here, the only difference is we've changed the task to a void, and we'll do exactly the same thing. So now what will happen is this will crash the application and we won't go any further. So we will copy that, and where's the exception? So it's right at the bottom, which is kind of fit for purpose because that crashes the application. Crashed task void, and there's no point in doing to be honest, the crash task void, because we'll never get anywhere, and I can guarantee you that. So throw await void and throw void before throw void. In fact, that's now before throw await, which makes more sense. Throw void. Right, so now we'll get to the before throw void, it'll crash, and it will actually now crash just as if it was on the same thread, which should crash the application. So you see that's the first throw that works its way. This is now the second throw. If we look at the call stack, we're at the second throw. So if we now look, we've done the before and after that, we've done the before a void, but now importantly, they should crash the whole application, which now the application's in a break mode and it's crashed. So there's nowhere else it can go. So that's what's happened there. Is the exception is if you use async but there's no return type, it changes the way which exceptions happen. And also, again, it's more importantly, any exceptions that occur in an async void are rethrown like this. So if there's a synchronization context, the exception is posted back. So what that'll do is in a UI application, if the exception's thrown and the original caller was a UI thread, it'll be thrown back onto the UI thread specifically. And if not, it's thrown onto the thread pool, which is the thread it's running on anyway, so kind of the same issue. But that's exceptions for you. That's kind of a point there. So the only real thing left is to show you the slight differences when it comes to WPF applications. So I'm just going to spin up a new WPF application, and we'll go from there. So it's just a blank WPF application. Let's just change the main window to have a stack panel, have a button in, content, click me, and we'll just do a click event for the sake of what we're doing. So you can see we've got click me. We'll go behind, and we now have some button to do something. So if we just run this now, the only thing we really need to prove and show here is the difference in awaiting inside of a function on the UI thread, and that, you know, the differences of what that means. So we've got the button here. There's no hover effect, but you can see here's hover. So this is the UI responding, and then we click and we run this function. So let's first show some kind of locking synchronous call. So let's just do thread.sleep. And I'll show you this is what happens when you do synchronous work on a single threaded application. So you got this, you can see the hover effects. I can drag the window, click the button. Now the window won't move, no hover effects, and then 5 seconds later, it moves to where it was dropped, and I've got hover effects back. So click again, drag down here, it's not happening, no hover effects. 5 seconds later, it's going to appear down there. So you can see basically it's like the Starbucks owner, where once you give it a task, in this case go asleep for 5 seconds, nothing else in the world happens until that point. So this is what makes the UI unresponsive when you're doing work. So this could be downloading something from the internet or processing some calculation. And this is why people end up getting slow UI when they're saying, why is my UI not responding? And it's because you're running it on the same thread. This is the UI thread. So let's start by copying over the helper method to first just log something out to the console. In this case, we'll change it to debug so we can see, or to be honest, let's just make it, well, no, we'll do it to debug. It's easy enough. So we'll write the message to debug. So now we've got the same thing. So now we can say log, do some work, and then log finished doing some work. So this is doing synchronous work on UI thread. To be honest, that can be at region and end region, and we can put a little private boolean do synchronous work equals true for now. Whether to do synchronous work on UI thread or not. And I can wrap that up, why not? And that'll be Cito, might as well clean it up. And then button click, helper functions. Right, so we now have, if do synchronous work, do some synchronous work. And we should be able to click the button and see an output down there. And then we click the button, you can see do work on thread 1. And then when it's finished, then it's finished work and this responds. And you can also see that this window moved before that kind of log outputted, because it had a lot of queued up messages while this was asleep. And then this got posted to be done after. So that's normal synchronous work. So I'm going to change that now to false, and we'll do some asynchronous work. which is the main thing we want to show. So we'll first do the same kind of action. So to do synchronous work, we turn this event handler into an async void, which, as we know from the description in the last project, that this means any exceptions thrown here now will bubble back up to the synchronization context.post, which will also end up crashing the UI thread. So to first show that a crash there does, we'll just do throw new exception, or rather throw new argument exception. Oops, spelled differently again. And if we ran this on the UI, it'll just instantly, when we click, can I get this to stay where it is? If I click this button, it will crash, and then the whole application dies. So we know crashing on the UI thread crashes the application. So now we've got an async void. We can now do, let's just say, await task.delay, which is the synchronous counterpart, if you will, to thread.sleep in a sense. It's basically used to do nothing, if you will. But as we know, it means do nothing on a different thread. So what we can do here is, in fact, I should have just put start synchronous work, end synchronous work. And then start asynchronous work, end asynchronous work. So first thing is, let's check out what thread this now runs on. So start synchronous work on 1, and we resume, now you can see, on 2. And that's important because if we copy over the do work method, which we can see the difference in the behavior, if we were to paste this in, and instead of delay, you just do work, and do async work, we'll now see more output in the log, which we need to, no, we don't, it's calling log, that's fine. So in here, we clear this off, click the button, you'll see starting asynchronous work, doing work for async 1, as we mentioned, because when you first enter before the await, it's run on the same thread, so this is UI thread. Then it does work for the inner thread, so this bit on thread 4, so it's no longer on the UI. Then it waits, and then it does the work afterwards on another thread. But then importantly, the difference is do work for async, or done work for async here. The bit after the await is called the synchronization context and resumed on thread 1. Now, if you compare that output with doing that exact same work on the console, then what you'll find is, if we swap back over to the WPF output and this output, oh yay, and we want to show that, there we go. So we have the same in effect on any of these. So you've got do work for whatever, which is 1, it's on the first thread. Do work for inner thread, which is here, on 4, and I don't know if I can find one with exactly the same threads, just to kind of show, not necessarily, no. So it doesn't matter, you've got a different thread here, like 4 is 8, and you've got 4 is 5, and 5 is 8 there. So you've got your 2 pieces of inner work happening on 2 different threads. But then this resumes on 8, whereas this, because it's got a sync context, resumes on 1. So that's the important thing there, is this now is running on the UI thread because it's been posted back. And that's a key difference between if you've got a synchronization context or not in the application. It does make a difference to where your threads, what happens with the threads and what to expect. So if we were to do let's end the region there. If we were to do await and then something through here, or we wanted to edit the doing async work on UI thread. If we wanted to edit the button here, so we'd have to jump into here, give the button a name, my button. Importantly, my button.text equals, or my button.content rather, new content. You can see this should fail after, this should work after a second. So we're in here, we click the button, and after a second it changes to new content, because we're allowed to do that because we're on the same thread. So let's start showing the important differences. If we were to spin all this off, and even if we were to await it, it doesn't matter. We do await task.run. So we know this will now run inside a new thread. We also know that UI, based on the last video, can't be changed outside of a new thread. Anything other than the UI thread itself. So now if we run this, what we'll see is, we click this button, you'll see the work started on thread 4 because we're in a new task. So the work carries on thread 4. Then the inner work happens and it resumes on thread 4. Nothing very special, that just happened to be the case. It didn't naturally resume on a, the same thread for any special reason. It just happened to be free. But the important thing is that the call to myButton.content can't work because we're not on the UI thread anymore. So we know that obviously from the last video, and we know that that's the case. So that's just kind of showing it running purposely on a different thread. But the way that await works is that because it uses the synchronization context, that's what's allowing it to work. So if we were to do, and I haven't tried this, but I presume I can do it. If we were to set the synchronization context of this calling thread to remove it, if you will, so it's no longer going to make use of the UI special synchronization context, this should also now fail. I think, like I've never tried this, I'm literally editing the UI. So there we go. So because we've now destroyed the UI synchronization context before we await, it's now going to store this new synchronization context, which doesn't care about the UI thread. And then the await after now tries to resume on a different thread. And then we get the same error. So you can see the reason it's working is to kill UI sync context on capture in await. If you were to change the sync context, then it no longer resumes on the UI thread. Run some async work. Log it. Should resume on same UI thread. Thanks to synchronization context. So that's basically what it's doing. And all it's really doing is doing the synchronization context.current.post, and like I say, posting the work to be done. I don't know if they can just do it that way. Like invoke it manually for now. I don't know how many things it wants. There we go, just wants one, so that's fine. So you could post work here and then do myButton.content equals something else. And that would, do the same thing, if you will. You're posting back. That's all the sync context does. You post it back to the UI thread. So we should resume on the same UI thread. Set UI stuff. Log it. So that's the important difference, that if you, at the point at which you do your kind of awaiting, if at the point at which it captures the synchronization context, it exists, which it does in a UI. So again, if you were to do var UI sync context equals synchronization context.current, and we were to simply breakpoint and run here and have a look, compared to the console application that had none, the UI context has a dispatcher synchronization context, which basically finds the dispatcher of the UI and does a post to the dispatcher, which we spoke about in the last video. So that's what that's doing. And as I mentioned, you could, just to prove a point, you could capture the synchronization context like await typically would. You can kill it so it doesn't do it by default. And then we could fix it by doing UI sync context dot post, and then calling this inside of there and passing null as the object. And I've never tried this, but I'm pretty sure that should now work, because we've still done what the callback would have done. Obviously not as efficient as letting the await actually handle it, but you can see it's now worked. It's got to here, even though it's resumed work on thread 5. So we're now no longer on the UI thread here. I've simply posted it back to the UI thread to do the work for us. So that's worked. I'm not sure what would happen if we click again. It appears to have remembered. So at the point of setting the synchronization context, it's not altered it for the whole lot. It's somehow restored it, in fact, after this point. But that's just kind of proving the point that the synchronization context is the thing doing the work. So that would kill it if we did that. So remember UI context, which would be that. That would kill it. That works. We should resume, and then if not, that's how we'd post. So I'll leave those commented in just for your playing around pleasure, if you will. And that's the key difference. So the one thing I did mention that will do the same thing almost as killing this is if you weren't going to set any specific content up here. So you didn't care about, you weren't doing any UI stuff, so this wasn't happening, and you were just logging. There's no point in getting back to the UI thread here at a cost. So what you can do is you can just do .ConfigureAwait false to not bother coming back on the same thread. So then if we click the button, you'll see again, we start at 1, but we end up coming back at 5. So that's where, we don't care about the UI thread. What you will notice though is just because this ConfigureAwait false is here, it doesn't stop the inner call, which has an await here, from returning returning after this await on the UI thread. So if you're going to use ConfigureAwait, you also really need to pass that down consecutively, that every call that is inside the call you're configuring await to false would also then use ConfigureAwait to false. So you'd have to do it inside here as well, which kind of then partly defeats the point, but it's very intensive and very, you'd only really use this in optimized, when you're really trying to highly optimize something and you're working on the UI thread. But to be honest, instead of doing ConfigureAwait at that stage, I'd simply just spin it on a new task and just say, task.run, get off the synchronization context in the first place, and then you don't have to do this inside every single call. So I'm hoping this explanation has been useful. I know it's been a very long video and kind of a deep dive, but it's really important that you understand those concepts, and most people don't understand this much about tasks. They really don't fully understand it. It's very evident that a lot of people don't get what's going on. So even though this is a lot to take in, I'd highly recommend just watching this video multiple times, playing around with tasks, and really, if you understand this fundamental stuff, all the videos I'll do in the future on like simple methods or making use of tasks, I won't have to deep dive. I won't have to explain the point of things. I can simply show you how I'm using them and they'll make sense. I'll do a brief explanation saying, we're jumping off this thread because of this reason and we're doing this and we're resuming, but you'll fully understand an async and await, a task, continuing with compared to awaiting, not awaiting, when exceptions get thrown and why. It's all very, crucial information. Because like I say, using a task is very simple. You just simply, and that's the whole point of tasks, they're meant to look the same. So if you go and compare a synchronous call to an asynchronous call, really all there is to explain is that you do that and you return a task. It's kind of, there's nothing to explain. But the underlying thing that happens is the important thing. Understanding why this frees up the calling thread and why this would make your UI responsive compared to this one locking your UI thread, sort of thing. So it's more about the principle, but hopefully I've put a lot of time and effort into constructing this video, into constructing this explanation and being, the best explanation I can be for a complicated topic. If you want to support what I'm doing, I do have a Patreon page, patreon.com/angel6. Any support for what I'm doing is greatly appreciated. As usual, any comments or questions, leave them in the video and I'll get back to everyone. And, hopefully this video was useful for you guys.